All right, let's wrap up our induction and recursion slides. So let me scroll down way to the bottom. So the last thing we started talking about was verifying programs, and honestly, that's the kind of the goal of this class, just learn enough cool stuff to be able to prove that our programs are always correct. Let's keep on talking in that direction. So let's talk about recursion. We'd like to be able to prove that recursive programs are correct, and those are a little complicated. So we better learn some new terms. So the first thing that we could talk about is how to define stuff. We can make recursive definitions. That's a thing. That's kind of easier than a recursive algorithm. It's a good start. So we can define sets recursively. Let's talk about that. So let's define this set, we'll call it bal, of balanced parentheses. Oops, I don't know why that went away. So these are like strings where the parentheses are nice and balanced, right? Does that make sense? So we can define what it means to be a string where all the parentheses in it are balanced with this kind of recursive definition. Just making sure like you can never have a string that kind of looks like this. See how like this one is making it unbalanced? So we don't want to be able to have that kind of thing. So we can make a set of only balanced things. And so we can do that with a base case and maybe some recursive rules. So the base case in the definition form is called a basis step. So our basis is going to be that the empty string is a string full of balanced parentheses. That's technically correct, right? We're trying to build bal, which is a set of strings with balanced parentheses, and technically the empty string, lambda, has all of its parentheses balanced. There are just none, right? And then we'll use some recursive rules to help build up this balanced set. So we started out with at least one thing. We know this set at least has one element. It has this guy. But it might have more. So let's add more things. Here are our recursive rules. And it's always going to be like take something out and then put something else back in using that thing you took out. So here's a recursive rule. So if x is an element of bal, then take it out, put it back in itself, and then also put in that thing surrounded by parentheses. Put that back in bal. So it's like take the lambda out of bal and like shove some parentheses around it. And like that's another string of balanced parentheses. And then remember that lambda is the empty string. If you concatenate it with other things, it kind of goes away. So this is just empty equal to open parenthesis, close parenthesis. So it's like use this and that rule to build this string. And that's another string of balanced parentheses. And that is correct, right? You see how we're only building things that are valid. And you can keep using this rule, because now it's like we have something else that was in bal. We can plop this guy out and use the rule again and put some parentheses around it. And use that to build like, now we have another string of balanced parentheses in this set. And you can build a bunch that look like that, yeah? And then, so you can keep using this one all day long that just adds parentheses all around something that's already balanced. You could also do the following. You could be like, all right, if x is in bal and y is in bal, could be the same thing, could be different things, but take two things out of bal and then put back in their concatenation. That's also a balanced string of parentheses. That's saying like, okay, using this rule, you could take out this guy and then also this guy and like concatenate them together. And that will build you a set of balanced parentheses, like this guy first plus this guy at the end of it. Concatenate them. It's another string of balanced parentheses. See that? Just built using new ones. And so now you can take this one out and use this rule again, or like put things around it. You could use either one. And do you see how that's going to build every single kind of string that has balanced parentheses? You can kind of see where the rules came from. Like this was a concatenation rule. This was one of the rules where you put some parentheses on the outside. That kind of stuff. You can do that forever and ever and ever, and this will build an infinite set of strings that have this property of being balanced, where the parentheses are balanced. Okay? And so if you use just those rules, no more, no less, then bal contains all but, it only contains balanced parentheses, all the kinds of strings that would have it. Okay? So that's a recursive definition. Let's have another. So let's solve this problem together. Let's give a recursive definition for this subset of binary strings. So it's just a bunch of ones and zeros. That's what a binary string is. So we're going to pick out certain kinds of binary strings now. Let's say that we would like in our subset S to have all the strings satisfying the property where this is true about them. Okay? So S consists of all strings that have the same number of zeros and ones. So we can let's figure out how to make a recursive definition about this. So like the string 0110 should be in the set S, but like 010 should not be in the set S, because that's imbalanced, okay? So let's try to figure out all the ways to like generate these good strings and never these bad strings, okay? Let's figure this out together. So yeah, usually a good idea for your basis is to put the empty string, because like that's usually gonna satisfy what you're trying to satisfy. So like, are the same numbers of zeros and ones in the empty string? Sure. Yeah, so S can totally start out empty, and then you can add rules to like add to that slowly but surely. So we know that lambda's in the set S. And then there's a couple of recursive rules that you can think about. You have to make sure, because the goal of the recursive rules is to like take out one thing and add in more things. You have to make sure, like, assuming this thing was already in there, you have to make sure that the thing you're putting back in, you're building on top of it, also satisfies the property. So like, again, like this is what the rules always look like. It's like if X is in S, add something involving X, all right? What do we want to add that keeps the same number of ones and zeros? So if this string already had the same number of ones and zeros, I better make sure, like, when I add in back X with some stuff, like if I added a 1 here, this is now imbalanced, right? Because it was balanced before, I just added to another 1, and it's not like balanced off by a 0. So I better add like 0 concatenated with X concatenated with 1. Like that's another string that I could add. And now they're balanced, because like the 0 counteracts the 1 that I just added. See that? And then likewise, you should probably add in 1x0. That will build up new strings. Does that make sense? And then similarly, so that's how you can add a new 1 and 0 into your string somehow. And then also, this rule also kind of applies to this set too. It's like you can concatenate two things that are already in there. So if X is in S and, or how about we say it this way? This is a faster way to say that. If X comma Y are in S, so if X and Y are both in S, then we should add in X concatenated with Y to S. So if this one had balanced ones and zeros, this one also had balanced ones and zeros, then adding two things with balanced ones and zeros keeps it all added and balanced. Okay, so let's run these rules a few times. So like let's take out the lambda and like use this rule to add in 0 lambda 1 and 1 lambda 0, which the lambda goes away, 0 1 1 0. So we have those. And now we can use the same rules with this one. Like this one, we could use this rule again. Take it out, and we could make 0 0 1 1. 0 0 1 1, and then likewise the same with this 0 1. We'll add a 1 on the left and a 0 on the right. See that? That's a thing. We can add those in, and so you can use those rules a bunch of times. You can also start concatenating. Right? You have this rule as well. It's like if you have these two things, you have two things in S. Could be the same thing, in fact. You can add them back in. So let's see. How do I want to do this? Let's use this one and this one. Right? We can combine those now. They're still having balanced ones and zeros. 0 0 1 1. No comma, sorry. 1 0 1 0. So again, it's balanced. And so you can run that rule a few times, and each time you run it, you're building more elements into this set. And so now you have more things to run these rules on. It's an infinite set. It's beautiful. So that's a recursive definition again. So that, of course, leads to the idea of like doing this inside of a computer and doing recursive algorithms. So we better spell that out. Even though I know we've had a lot of experience with recursive algorithms, we want to hit them harder in this class. So what is a recursive algorithm? Well, it's an algorithm that is going to like run itself. It's calling itself, if it's a function, on smaller input values. Just like this recursive definition was building up bigger things from smaller elements that are already in the set. That's kind of how this is working. So recursive algorithms are very similar. Smaller is key. You gotta work on something smaller. When you call yourself, it's called a recursive call. Hopefully you've heard that word before. And I hope you've seen this before, like when I try to teach it this way, but like it's very similar. Recursion is very similar to induction. Like you don't have to do extra thought. You just get to assume that your recursive call really does the right thing. Just assume that your smaller recursive call really does work. And as long as you build up the answer using it correctly, it does. It really will do the right thing. All right. So let me show you factorial, because that's what everybody learns and studies with recursion. let's do factorial as an example. The base case for factorial, it could be like define 1 factorial to be 1, that's a thing. But actually, in math, 0 factorial exists. Can't go any smaller than that. So like that's the smallest factorial you can have, and 0 factorial in math is defined to be 1. So that's like your base case, and so that's your stopping point. And for your recursive case, usually what you want to do is you try out some examples and you see how it generalizes. So like 5 factorial, what is that? That's 5 times 4 times 3 times 2 times 1. And do you see a smaller factorial inside of this bigger factorial? There it is, right? So that's what you're looking for, and then you can try and generalize that and make sure it works for larger things. So this is like, consider this to be an n factorial. You're asking for n factorial in the general case. That's equal to n times n minus 1 factorial. See that? So there's your recursive case. But again, you need the base case to eventually stop it. That's the whole point. So there's your recursion. There's your smaller recursive call that you get to assume works. Okay? And so let me show you a recursion tree to show you like why this is eventually going to stop and it's going to do the right thing. It's going to really compute like 5 factorial if you run these two rules together. Because what is 5 factorial? Let's kind of draw how the stack is going to unwind and like make recursive calls. So 5 factorial, you can send that off to this problem. That becomes, using the recursive case, 5 times 4 factorial. And then 4 factorial, again, you can send that off to the recursive case. It's still not the base case yet. That's equal to 4 times 3 factorial. And you can keep playing this game. 3 factorial is equal to 3 times 2 factorial by the recursive case, which is equal to 2 times 1 factorial, which is equal to 1 times 0 factorial. Yeah. And then this one is finally the base case. Like, okay, you asked me for 0 factorial. I know the answer just once and for all. I can give that back. And then that starts unwinding. It's like, all right, now we have the final smallest answer. This is getting given back to whoever was asking for it. So now we know that 0 factorial is 1. Multiply that by the 1. And then our final answer for 1 factorial is 1. See that? That's kind of how that gets given back. So like this gets given back. We do that computation. This gets given back. So now we know that 1 was 1 factorial. Multiply that by 2 to give back our answer for 2 factorial. That's why we give back 2 there. That's why it's correct. And then this call, this recursive call to 3 factorial, is waiting on 2 factorial on its answer, so it can multiply its 3. And now we know that 3 factorial is 3 times 2. So that's 6. And it gives back 6 to the 4 factorial that was waiting on 3 factorial. It can multiply its 4 by that 6 to make 24. So let's do that. That's what's being given back, 24. And then this was 5 factorial, the original call, waiting on 4 factorial to multiply its 5 by that answer. Now it knows that answer was 24. Can multiply that by 5 to make 120. And now we know what the answer was, and we can do cool math with that or print it out. All right, so that's recursion in a nutshell. It's going to make its way down to the base case, and then work its way back up, back to the original call. And this is kind of like backwards when you draw the stack. Like the stack is getting taller and taller and taller down to the base case, and they all keep popping themselves off. And eventually the work is done. And it gets returned. The original call's answer gets given back. All right? So that's recursion in a nutshell, and I'd like you to practice it. So try to make this algorithm. Give a recursive algorithm, so it's required to be recursive, that takes a sequence of numbers, you can think of it as a vector, and gives back the minimum number in that sequence. All right? I know you know how to do this with a loop, but see if you can figure out the recursive algorithm to find the minimum in a sequence. Okay? So let's see here. So let's say that you're given a vector, or if we want to think about this in terms of bracket, let's say that we were given a list L as our parameter. List L, let's say. And what we'd like to do is, like, if you have something, if you have a sequence, and you're going to do recursion on that sequence, usually, this is going to work. This is the secret, if you didn't figure it out. Usually, you recurse on your sequence. That's the verb form of recursion. You recurse on it. You recurse on the length. That's the thing that's getting smaller. On the length of the sequence. So you split it up into like the first element and the rest of the sequence. Or the first part of the sequence and then the last element. So either this kind of way or this kind of way. Either one works. And so let's say we were given this sequence, this list in Racket, let's say like 8, 6, 7, 5, 3, or 9, my favorite list. What you can do is you can break that down, at least as far as Racket is concerned, this is the easier way, into the first element. There's like a legitimate function called first that gets you that. And then this is the rest of the list. All right, so that's the rest. And then our goal is to like compute the minimum here. And so this is a smaller list that we can call our recursive algorithm on, okay? Recursively, we're going to go and find the minimum of this list, okay? So it's going to be what we do, and we can assume that it's going to do the right thing. So rest, the recursion on the rest, finding the minimum, we can assume that's going to give us like the 0 back, because that's really the minimum in this list. We're going to assume it does the right thing. So that gives back 0. And then you take that and you compare it with your first, right? Because like maybe this was -1. You don't know which one's smaller, either the smallest thing in the rest of the list or your current first element. So it depends. So you look at this guy and this guy, the result of the recursive call and the first element in your bigger list, and you pick which one was bigger. Like you compare this guy to this guy, and then you give back as your final answer, okay, the minimum of the two. Okay, 0 was the smaller, that means 0 was the smallest thing in the whole list. Okay, so that is your recursive case. So what you want to do is you have a smaller list, that's what you're recursing on. You get to assume that your algorithm's going to do the right thing on it. So recursively find the minimum of the rest of the list with one less element, and you get to assume that's going to give you back the correct minimum of the rest of the list. And then you take that and you compare it with your first element, because that's the one thing the recursion did not look at. And then whoever wins out, whoever's the smallest thing, is what you return. So that's your recursive case, this kind of diagram. And then we also need a base case. So the empty list cannot be the base case, the empty vector, whatever, cannot be the base case because like you have no number here to return. I guess maybe this could be your base case where you return that the minimum is positive infinity. That's possible, but that's a little too much work. So I think the better way to do it is like have your base case be a single element list. Okay, what's the minimum of all the values in this single element list? It's the one value that's inside of it. You see that? So I think that's better. So base case, let's have that be when the list is 1, rather than having to do something weird with positive infinity. I think that would be the better way to go. So here is that actual algorithm in Racket. Let me run it for you. It's this part right here. So here's your min list. You give it a list L, and you have either base case or recursive case. So if the length of the list is 1, then that one element that's in your list is the minimum. Just return that. Otherwise recursion. So recursively find the min of the smaller list. So here's me calling my function, min list, on the rest of the list. Rest gets you the one, chops off everything but the first element, gives you the smaller list. And so there's the recursive answer, and you need to compare that to the first thing in your list. It's like, which one's smaller? Get the minimum of those. So like, if the first of our list, the first element is actually smaller, like this was maybe like a -1, then really the answer is -1. See that? That is the smaller thing. It's the minimum of the whole list at that point. So return that if it's smaller. Otherwise, if it was greater than or equal to, then the rest of the list is the right answer, just like it was here, because 8 was bigger than 0. We want the min. So that's that. And so this answer should be printing 0 back to us. Let's confirm that. Oh, suspense. And actually, let's see. I'm also printing every time I'm calling it, so you can watch the recursion unwind. It's kind of cool. So there's that. So you're watching it. Let's see if I can zoom out there. So you're calling it with the whole list. It's recursing, chopping off one element at a time until it gets down to the base case. See that? And then it unwinds. It's like, all right, the minimum of this is 9. Minimum of this is 0. Minimum of this is 0. Minimum of this just keeps on having 0 for the rest of time, because then it finally finds the real minimum. It's like 0. That's the answer. Isn't that cool? So, oops. That is our first example. Hopefully you got that perfectly, or you got very close. So there's that. Let's see. We're going to remember to come back when we talk about binary search. That's our next example here. So, induction and recursion, like I was kind of saying here, just like with induction, you can assume things. There's a very strong correspondence between induction and recursion. What you do is you use induction to prove that your recursive algorithms are correct. All right, so that's the goal. I just said that. And so what you do when you're using induction, there's always the thing that you're inducting on, right? I hope we have spent enough time on that. Where is the first time we talked about induction? It's like for all x p of x, you're kind of doing that, and it's like it's a number. You're trying to prove something for every number. So you're like, there is a size of something. There's a number that you're doing your induction on. It really has been like numbers so far, but you can think of it as like the size of a list. It's totally a thing. That's another number you can work with. So you always must specify the number that you're inducting on, because it really is, you're talking about numbers when you're doing induction. And that number better be getting smaller, even if it's like a generic kind of size of something. And so even if we don't like write it, we always need that predicate, p of n, at the end of the day. That's what we're recursing on, right? That's what we're inducting on, we say. So n is the thing that's getting smaller. That's the goal, all right? And we're kind of building up backwards. So in our recursive algorithms, here's our hint, always do induction on the thing that's getting smaller in your recursive call, because like that's the thing that's going to eventually hit to the base case, and you want that to be like your p of 0 at that point. So that's what you're going to do your induction on, okay? So let's do some proofs that our recursive algorithms are correct. Let's make an example. Let's do factorial. So here is the idea. Factorial is, first of all, what is our proof? We're trying to prove that our factorial function correctly computes the mathematical factorial. So like our p of n is like, we're trying to show that for all n, p of n is true. So like p of n is that, like our factorial function, like this one, factorial of n really is, and it returns the true mathematical factorial of n. Like that's, we want to prove this for every n. Does that make sense? It is a for all proof. So for factorial, at least, in the recursive call, it is the number itself that's getting smaller. So that's what we're going to do induction on. We have to say what we're doing induction on. So we're going to prove this by induction on the parameter n. Okay? So now watch me. And we're trying to show that for all n, this is true. For all n p of n. All right, so we say proof. And then usually we, like, just like when you say you do a proof by contradiction, you try to specify that. So we're going to say proof by induction on n. And again, we have a base case and an inductive step. So what's our base case? It matches the base case of the recursion. So it's like we want to prove the smallest thing for this. What's the smallest n for which this works? And that's 0, right? And that's 0. That's our base case. We want to show that the base case really does return the right answer. So that's when n is 0. We just have to show that 0 factorial, right? Factorial of 0, whatever that returns is equal to 0 factorial. And both of these, do you see how when n is 0, this is going to return 1? So that's 1, and we know that 0 factorial is defined to be 1. So that's our proof there. So that checks out, QED for the base case. And then we have our inductive step. Inductive step. We have to show that p of k implies p of k plus 1, right? Just as usual. Assume, and that just has to do with the correctness of an algorithm at this point. It's nothing new, just a different setting. Assume the smaller call works. That's your p of k. And then what we want to do after that is then prove the original call is correct. That's your p of k plus 1. P of k plus 1. Okay? That's a k right there. So, what does that imply? First of all, it implies that n is greater than 0. All right? That's like our n greater than 0 case, which means we hit the recursive case. Like we're going to end up running these two lines instead of this first line. And so we're going to reason about that. All right, so, okay, if n was greater than 0, we're going to ask for the factorial of n minus 1. That's our smaller call. All right, so by the inductive hypothesis, we're assuming that the smaller call works, because like we're being called on factorial of k plus 1. We can use the fact that factorial of k works just fine. That's our inductive hypothesis. It's like the smaller call is okay. It gives back the right answer. So by the inductive hypothesis, this call right here really does give back the true factorial of k, which is n minus 1 in this case. It really does work out, and I don't know why I can never erase. There. So by the inductive hypothesis, this r value, this variable, r is equal to, it's going to be equal to factorial of n minus 1, and like we're assuming that n is k at this point. So r is equal to n minus 1 factorial. We get to assume that the smaller call works. See that? We get to assume that r really holds the mathematical n minus 1 factorial. What we need to show is that our final answer, what we return, is in fact the original n factorial. We need to show that we return n factorial. So, okay, what do we return? We end up returning r times n, yeah? We return r times n, which is equal to, well, we're assuming that r really does hold n minus 1 factorial, and we're multiplying that by another n, and just by math, right, n minus 1 factorial times another n is n factorial. And that is exactly what we end up returning. Do you see that? Do you see how we reasoned about that? You get to assume that the smaller factorial works because of induction. That's our smaller call. That's our p of k. And our original call was p of k plus 1, one more. So you can go and look at the previous call and assume it's going to do the right thing. It's going to hold, this predicate will hold for it. And that's the beauty of induction plus recursion. Isn't that so nice? So that really is our proof. Recursive factorial is correct. It's going to compute the right answer, assuming n was non-negative. If n is negative, then all bets are off, right? Because this will just infinite loop. But we've proven it, like when n is 0 and n is greater than 0, under all these assumptions, it all works out. So that's our first example. Let's do another example before I ask you to try it. So here's a function called reverse string. Okay, it's going to take a string and compute the reversed string, right? Not too hard. It's like if you give it ABC, it gives you CBA back. But let's figure out how it does it. All right. So we're going to prove by. Well, let's discover like why we need to do that. So let's run this example. Let's say that we're gonna input the string ABC to our function. What's it going to compute? It's going to try and compute CBA, but let's see how. So if S is empty, it's going to return the empty string. That's fine. And then otherwise, here's how you read this. So let C be the first character in S. That's like the A. It's going to pick out the A, remove it, and then like it's going to split it up, and it's essentially splitting up the string into A and then BC. And then it's reversing recursively the rest of the string, the smaller string, because you remove the first character from it. And so you get to assume by induction, right, by the magic of recursion, that, which is just induction at this point, that it's going to do the right thing. It's going to correctly reverse that string. So now you have CB. And then you take that new reversed string and you tack on this character that you left out. You take it and you put it right there. And that is what you return, CBA. And so that's kind of why it's working, okay? And so this is an algorithm that takes a string. A string is not a number, so we have to do induction on some number. What's getting smaller? It's the thing that's being smaller in the recursive call. Do you see how the string itself is getting smaller in the recursive call? And the number associated with that is the length of the string. So that's going to be what we're going to do induction on. We'll do induction on the length of that input string. All right? So it looks like our base case here is empty string, so that just screams that our base case for the induction should be empty string. So base case, how do we know we have the empty string? It's when, if we're doing induction on the length, it's when the length is empty, right? Length is 0. Length is 0, that implies that S is the empty string, and what we return in the case of the empty string, we return the empty string right back, and so all the characters in the empty string inverted really is the empty string still, so QED. There's no difference. So the empty string is its own reverse, so that's fine. And now in our recursive case, or in our inductive step, we're going to consider the recursive case. So in that case, S is not empty. It's greater than 0, so it's equal to. We can break up our string into S as like the first character, let's call that A, concatenated with like the rest. First character and the rest of the string. Okay, the rest of the string could be empty. That's fine. So let's run, assuming our string looks like this, let's run the recursive case. So C is the first character, so let's like C is the A. C is the A, and then the rest is like that. And then, so like the string becomes just R at that point. We removed C from S, that's what happens. And then S prime is the reverse string of S. We're assuming that S prime holds whatever R was, but in like reverse order. And, S holds this result of this call. But remember what we're doing recursion on. We're doing induction on the size of the input string. So this is recursion on a smaller string. We get to assume that it works, right? It's our P of K implying P of K plus 1. This is our direct proof all over again. So just like this one, we get to assume that the smaller call works. You have to prove that the original call is correct. So we get to assume that this call to reverse string on S really does like give you back the true reverse. Let's write it like that. This is R in reverse. Okay, that's what we're holding in S prime. Assume that that works. And then S, the final answer for S is going to, and we get this by the inductive hypothesis, we get to assume that's going to really reverse that smaller string. And then S becomes whatever S prime was, which is the reversed thing. There, it becomes S is S prime concatenated with that C, which is our A here, right? The C, which is our reverse thing concatenated with the A character. And just like by the definition of reversing things, like what it means to reverse something is to take and reverse everything that came after it and then plop it at the end. This is like what it means to mathematically reverse something. And so now we know, like this is now in order in that way, from right to left. So this really does reverse the string correctly. So it's what is being returned is S, and that is correctly the reversed string. Okay? That's kind of how you go about these proofs. So I've shown you some examples now. I want you to try. Try to use induction to prove that this function, this min-list function that we were using here, this algorithm to compute the minimum of the sequence, is going to really work for every like non-empty sequence of numbers. All right? And as a hint, your inductive step should have two cases, because do you see how the recursive case here is having an if statement? You're not sure which one you're in. You're not sure if you're going to run the body of the if or the body of the else. So you have to like have cases for both. So all right, did you see it? So again, like the proof is, the theorem statement is like the minimum of the sequence correctly outputs the minimum, right? The mathematical minimum of all those things. So base case, and what are we doing induction on? We're doing induction on the length of the list. That's the thing that's getting smaller across the recursive calls. Okay, so the base case, again, if we're doing induction on the length of the list, we have to consider what the length of the list is in our base case. That means it's 1, right? If the length of the list is 1, we're in our base case, and we have just one element in our list. And what we do is we give back the one and only element, right? Give back the only element. Because by definition, like the minimum of a one element list is just that one element. Nothing there. It is the one and only thing, so it is the smallest thing. Okay? And then in the inductive step, well, we know we're not in our base case, so the size of L better be greater than 1. Okay? Size of L better be greater than 1, and what does that mean to you? What does that mean for us? That means the list really does look like something concrete at the first element, and then concatenated with the rest of the list, and the rest of the list is non-empty. All right? So that's that. And so that means you could make a recursive call on the rest of the list. That is a smaller thing that you could call our function on, because it is a non-empty sequence. All right? So what we do is we're going to make this recursive call, and min-rest holds the minimum of the smaller list. It holds the result of the recursive call to our min list on the smaller list. And by induction, right, by our inductive hypothesis, we get to assume that the smaller call works, because it's our P of K, and we're trying to prove P of K plus 1, the bigger thing. So we can assume, just by our inductive hypothesis, min-rest, that variable, correctly holds the min of the rest. Okay, And then, all right, with that in mind, now we're going to run this if statement, and we're not sure which branch we're going to take, so we better have two cases. So case 1 is when the first element of our biggest list was smaller than min_rest. So if first, so that's what our list broke down into first concatenated with rest. If first was less than min_rest, and min_rest was correctly the smallest thing, the minimum of that smaller list, first was something even smaller, then, well, the minimum of the whole thing is first, and that is what we return. See that? So check mark for that case. That checked out. That works and does the right thing. And then case 2, well, that means this wasn't true. This condition wasn't true, and so that means first was greater than or equal to min_rest. And at that point, like, min_rest is the one you return. That's min_rest is being returned, and it is correctly, like, if that's the smallest thing and the rest of the list in first is at least that, by returning min_rest, you are giving back the smallest thing. And so again, that is correctly doing the right thing. And do you see how that is proving, beyond a shadow of a doubt, no matter what the list looked like, it's giving back the right thing, and we are showing that with induction. So when you're, I guess like the way that I write my recursive algorithms nowadays is I'm doing induction in my mind. Like that's what it means to like assume that the recursive call works. You're doing induction like as you're writing your algorithm, in a sense. And so this is what I'm thinking about, and so it's like it's obvious that it's going to work out. But if you needed to spell it out like this, this is the reason why the induction is doing the right, or sorry, why the recursion is doing the right thing. So hopefully that makes a little bit of sense. Please yell at me about this stuff, important stuff for sure. Okay, let's talk about the time complexity of recursive algorithms, because that's pretty difficult. This is like, it looks a little weird when you're trying to ask for the time complexity of an algorithm. But in general, what is the time complexity of something? It's a function. It's a mathematical function that like takes the input size and gives back like the number of basic operations performed by your algorithm. All right, on that input size. Okay, so for a recursive algorithm, this idea it's kind of defined in terms of itself. So it's defined in terms of smaller calls to t, where t is asking for how many steps a recursive call takes. And so it's going to use a recurrence relation, which is weird to think about, but kind of makes sense. It's like, all right, how long does it take to call this n, call our function with n input size? Well, it's going to take like constant time to do one thing, like an if statement, and then we're going to make a recursive call. So we're going to like add on like how long it takes to do n-1 things. And like this is an equation now that we have to solve. Okay, it's very weird. So to analyze this time complexity, we're going to create a recurrence relation for the number of operations, and we try to solve it. Okay, so let's think about like what is the recurrence relation for the factorial function. Okay, and I'll show you how to solve it in a little bit. So you can just think of like this means O of 1 or something, theta of 1, and so I'll write it like that. How many operations does it take to do factorial, basic operations wise? This one. So okay. For factorial, what are we going to do? In the recursive case, let's say we're trying to solve the recurrence relation for the recursive case, because that's the one that's going to happen the most. So factorial, then, we are going to do like, we're going to check in the recursive case, we're going to check a condition, it's going to be false. We're going to make a recursive call. That's, all right, so let's think about the timing of all this. Maybe I should make some notes here. Where do I want to put this? So like this is one basic operation to check this guy. Oh gosh, one basic operation to check this, and then we're going to make a recursive call here, and that's going to take as long as factorial of n-1 takes. So that's like t of n-1, how long it takes to run an n-1 call, and then a return statement. So that's like one basic operation, another one basic operation, and this is recursively smaller a number of basic operations that we have to solve for. All right, does that make sense? So it's like constant work on top of a recursive call to n-1. Okay, so that's kind of how you write this recurrence relation. That really is this kind of idea. So let's see here. This is it. What is the number of basic operations to run factorial? Well, you're going to make the recursive call, so it's the number of basic operations to like call the n-1 version. plus like a constant amount, so let's just say 1, it's really like 2, a constant amount of basic operations to like do the if statement, to do the returning of the answer after you do the multiplication. So it's like, essentially, it's the recursive call plus a multiplication. You can think of it that way. And it's like, this is how long it takes to solve, or to do factorial of n. It's like how long it takes to do the n minus 1 factorial, plus the time it takes to do the 1 multiplication, let's say. And so this is the equation. We have to solve that. What does that even mean? Is that O of n? Is that O of n squared? How do we do that? So that's one thing we have to worry about. And then let's also talk about, before we get there, I'll show you how to solve this. Let's also have some other nice recursive algorithms in our tool belt to talk about, because I want to like show you how to analyze them all at once. Let's talk about divide and conquer algorithms. This is a term that means you're solving a problem recursively. A divide and conquer algorithm is a recursive algorithm, and what it does is it breaks up the original input. It's usually like you're given something that can be broken up in like half very easily, like an array of something. And so what you do is you're breaking it up into like half. And you're like, here's your input, and you're breaking it off into perfectly half, like roughly equal size, and you're recursively solving these subproblems. Recursively of equal size. Okay? So that's the idea. So like this is what is t of n, but not supposed to be an n, sorry. What is t of n, but however long it takes to solve this one, that's t of n over 2. Like the size is now n over 2, right? This is another t of n over 2, however long it takes to do that. That's kind of what we're going to look into. Let me show you an example in Racket of a divide and conquer algorithm. We're going to do binary search, all right? Which I don't consider to be divide and conquer. A lot of books do not consider binary search to be divide and conquer algorithm, but your book thinks that it is, so we're just gonna assume that it is. But remember what binary search is all about. You can do it recursively. It's like in binary search, like what you do is you look in the middle of your sequence and you're like chopping off half of it always. Like, all right, is the thing that I'm looking for bigger or smaller? If it's smaller, you can chop off half of it. It's like, all right, now I have this half-size sequence to go and look through. And you'll look in the middle of that, and you'll like chop off half of that in the other direction maybe. And like you keep on doing that as long as you need to until you find the thing you're looking for, until like you exhaust your array. So that's essentially the idea. You can do binary search recursively. If you haven't seen that before, you just look in the middle of your current sub-array that you're trying to work on, like this one. If the middle is what you're looking for, you found the thing. And then also, if you have no array left, like you've chopped off half too many times to have a whole element left, then you're done. But in the recursive cases, like if the thing you're looking for is smaller, you have to like chop off the right half of the array and search on the left. Or if the thing that you're looking for is bigger, you're going to chop off the left half of your subarray and go and look on the right. But it's, again, recursive, right? Because you're still searching. It's still the same idea. You're going to binary search through a sequence that is sorted. It stays sorted, it just gets smaller. And so because it gets smaller, that means you can use recursion. It's the sequence size again that's getting smaller. So in Racket, here's that. So we're binary searching for, like in a vector, let's say, for a value. Vectors exist in Racket, so let's use those. And I'm going to, like this is how the user might call it, but I'm going to have a helper function that actually does the binary searching. So it's like binary search helper takes 4 things. It's going to take, well, what it means is we're going to search for this value in V, and V is a vector, and we're only considering the subvector between start index and end index. So at the very beginning of time, like we're searching the entire vector, so between index 0 and size -1 for the value. But as the recursion happens, we're eventually like going to make this these indices change. Like it's going to be like between 0 and half, or between like a quarter and a half, or something like that. The indices are going to get smaller and smaller. These are going to change, all right? That's going to like make our sub vector that we search through. And so again, I'm going to shout out when we're searching through it. Let me comment this guy out. And so this is the recursion. This is where it's all going to happen. And so in the in this algorithm, in this recursive algorithm, we have to figure out if we're in the base case or not. So we're in the base case if our search space is empty. So between start and end index, if like it's like if we're trying to search between indices 4 and 3 in that order, there is nothing in that order, and so that's like invalid. So we'll return -1 to mean like we didn't find the thing, because again, the job of binary search is to return an index. -1 is an invalid index, so we're done if there's no array left. That's one base case, and the rest are going to be in this else case. Like if we have a valid search space to go through, then let's look in the middle of that. So this is the racket way of looking in the middle. It's like, all right, average together the start and end indices, divide it by 2, do integer division. So this is halfway between start and end. That's our middle index. And then the middle value is going into the vector at that index, right? That's like, this is the function that does that in racket. It's like go into the vector at that middle index. This is the mid value, all right? And then we'll compare. Like, is the thing that we're looking for smaller? The value that I'm looking for, is it smaller than mid? If so, I need to chop off and look in the left half of the array, right? I need to look between start index and like end index was too big, right? All the way to mid index was actually too big. So I want to go from start index to mid index -1. That's the only place where it could be. Does that make sense? That's the secret. And then likewise, if it's bigger, like if the thing I'm looking for is bigger, then I knew the thing at the midpoint was too small at that point. So like the places where it could be is like bigger stuff. So it better be like mid +1 all the way to end. That's our new search space to go through. So that's how we chop off half the array each time, or half the vector. And eventually, we're going to get down to either the base case where there's nothing left, or we're going to end up looking in the middle and like, oh, that was the thing we were looking for, like else. It's not smaller, not bigger, it's just right. So at that point, we found the thing we were looking for, and we can return that index back. So that's binary search in a nutshell. And so let's, it needs a sorted vector, of course. Let's search for 4, and then I'll search for -4. And we can watch it work. Oh gosh, I did not mean to. Oh gosh, cancel abort. I want to say racket recursion. There we go. And so here is how it's working. It's making a smaller vector. So originally it's searching between all the indices, and then we're looking at 3, but we're looking for 4. And so it needs to look in this half of the array. It notices now. So it's going to search between indices 3 and 4 for 4. And then it finds it because the midpoint is going to it's going to do integer division, and so it's going to hit the smaller one. It's like, oh yeah, I found it at index 3. But if the thing you're looking for is not there, let's say we're looking for -4, then it's like it's going to keep getting smaller. Like, oh, it's smaller than 3, so I'm going to search between 1 and 2, indices 0 and 1. And then it's like, oh, I'm going to look in the middle of that. I see 1. That's still too small, so I'm going to search between indices 0 and -1. So that's kind of how it runs out of room. It's like, oh, that's where it should have been, but this is now an invalid search phase. So it's going to hit the base case and be like, no, I don't find it. It's not there. And so that's binary search, divide and conquer binary search. Another example is merge sort. That's like your standard divide and conquer algorithm. And I want to teach you how to find like the recurrence of that, and we'll figure it out together. We'll solve for the running time, which you maybe know from a previous class. So merge sort, this one really is divide and conquer. The idea is like you're taking something that is not sorted, like you have an array or a vector, some sort of sequence, like 4, 2, 3, 1, and you're going to chop it in half. This is the merge sort algorithm. You divide it in half, and you recursively conquer both halves. Like you chop this off into 4, 2, and 3, 1 subarrays. And the magic of the recursion, these are smaller arrays now. You're going to recursively sort them. You get to assume that the sorting is going to work. This gives you back 2, 4. This gives you back 1, 3. And then you're supposed to merge them back. Like you go through each of these, and you're like, all right, I need to put back all this together into 4 things. And like you just start at the start of each of them and like take the smaller one. It's like, all right, the 1 versus the 2, the 1 wins. 2 versus the 3, the 2 wins. 3 versus the 4, the 3 wins. And then I've taken all of this one, so I'll take the rest of this one. So I'm just bringing the 4 now. And so it's very simple once that's done to merge them back together. And so let's talk about that, and then we'll try to solve for things. All right, we'll try to solve for recurrences and things. So I'll comment this out. This is merge sort, by the way. So everything I just said, this is it in code. It's a bit complicated. Maybe go back to your 41 textbook. That's what I would suggest. But this is the merge sort algorithm. Let's say that we're sorting a list, and it's recursive, and it has to do like with the size of the list, right? So here's the size of the list. So I'm going to define a variable to mean that. And if the size of the list is less than or equal to 1, then the sorted version of that list, like if it's empty or has one thing in it, it's already sorted, right? It's ready to go. So that's like half of the size. We're good. We're done here. Otherwise, we should chop it in half, right? Otherwise, like if it's 1 or less, then it's already sorted. We're good to go. Otherwise, chop it in half. Let's figure out half of its size, and we'll split it up. So there's like a take and a drop function for Racket that takes like a bit of things and makes a new list. Gets rid of a few things and makes another list. So here's the left half and the right half. Then I'll recursively sort them, and then I'll merge them back together with a helper function called merge. All right. So here's my helper function, and what I do is this is just like a loop. It's just like checking and seeing if anybody's empty. Go to the left, go to the right, and just like take the things in order. So feel free to read these comments. But this is doing the right thing. It really is going to sort the thing. And you can kind of watch it work, and it gets down to the base cases and builds itself back up, and it really does give back 1, 2, 3, 4 from 4, 2, 3, 1. So it is doing the right thing, but I'm more interested in teaching you how to analyze this. All right. So how long does it take to divide the array in half? Like you're going to make 2 brand new arrays, essentially, or lists. And so you're going to go through all the lists. You're going to go through the whole thing and add them, right? So that's going to be a linear time thing to make this size and this size, right? It's like you're doing pushback on a linked list. It's just linear work. And then you're going to recursively sort each half. We don't know how long that takes, but it was like if we're of size n, the time it takes to do half of the sorting, it's n over 2, t of n over 2. And we're doing that twice for each half. All right? And we're going to merge them back. And that, if you kind of understood what I just said, it's going to be a loop. It's going to be a linear loop through both of those lists. You never look at anything after you've seen it already once. So that's linear stuff. And somehow all these things together lead us to an answer. So let's figure that out. Okay? So the secret to solving recurrences and figuring out like how long it takes to do something is one way that your book talks about, and that's the way that I'm going to hit hard in this lecture, is to draw a tree. So let's do the recurrences for factorial, binary search, and merge sort. So for factorial, the time that it takes to run factorial of n is like you got to make the recursive call to factorial of n minus 1. That'll take some time, however long that takes, plus constant work, right, to do like an if statement, to do a multiplication by n after you get back that recursive answer. Okay, see that? And then this one is like this is the time that it takes to run the recursive case, and then the time it takes to run the base case of factorial is just like do the if statement to notice that you're trying to take the factorial of 0, and then just return 1. And so that's going to be constant work, just a if statement and immediately return. Okay. For binary search, what's its recurrence? Well, you're given size n. What's the time that it takes to run binary search on a array or vector of size n? Well, it's going to be constant work to look in the middle and then either go left or go right. And so what you're going to do is you're going to binary search in the recursive case on half the size of the array after picking out which side to go down. So constant work to pick which side to go down, and then this is how long it takes to run binary search on that half-sized thing now, because it's going to be chopped in half. Okay? And then again, the base case for binary search is like your search space is empty. Just like notice that with an if statement and return -1. So again, that's constant work in the base case. That's usually what's true. And then for merge sort, what do we do for an input of size n? Well, we're going to make a recursive call twice, right? In the recursive case, 2t of n over 2 recursive calls. So do the work on half the thing twice, recursively sort twice, and then merge those both things back together. Merge both of those things back together, and also divide the array in half in the first place. That's like O of n plus O of n, theta of n plus theta of n. So that's just n again. It's like 2 times n. But that's still theta of n work. So that's the recursive case's recurrence. And then again, for if you're trying to merge sort something, like you're trying to merge sort a size 0 list or vector, then like it's already sorted. The empty thing, you just give that right back after checking its size, so it's constant again. So these are our recurrences for both the recursive case and the base case. And now let me show you how to solve for these with trees. Let's do factorial. That's the first one. That's the easiest. So, like, we got to break this down. What we're trying to solve for what t of n is. Is that O of n? Is that? I think it is, right? Let's make sure. So t of n, what is that? So at the t of n level, I'm going to like do my I'll do a recursive call, and I also need to like do an if statement, some multiplication. But like at this level, I'm going to do constant work at the t of n level, and I'll pass off some of the work to the t of the n minus 1 level, right? This is going to be passed off to t of n minus 1. See that? And how much work does that take at that level? Again, it's this guy. It's going to take, well, constant work at its own level plus t of n minus 2 work, right? So again, it's going to hand off the problem to t of n minus 2. And again, that's going to take constant work at its level, again, if it's the recursive case, plus t of n minus 3 work to be done. So down to t of n minus 3. You see what it's going to do? It's going to be doing constant work at each level. And then the question is, how many levels are there? It's going to get down to t of 0, right? Just likewise, I think you can imagine like t of 2, one thing to do. Pass it off to t of 1, one thing to do. Pass it off to t of 0 finally, which we have determined is the base case, and we've defined the amount of work to be done there is, again, constant. And so like this is kind of the tree for how much work is being done in each level. Do you see how I kind of came up with that? And then the question is like, how many ones are there? Because you're just adding them all up. And so the height of this tree is, let's see, the height is n, right? The height is n, and you're doing constant work n times. And that becomes n times constant work. That is linear time total. And that's one way to solve this recurrence, to figure out what is the time complexity of recursive factorial. And so it's just as good as the loop. It's perfect. So that's that one. Then let's try to solve for binary search and for merge sort. Okay, let's figure those out together. For binary search, well, we have, again, in the recursive case, if we're given initially t of n, what do we have to do? T of n. That's always equal to t of n over 2 plus constant work at the current level. Constant work at the current level plus half the work, or we go down half a level, like we're chopping our work in half. So again, in the same style, we're starting off trying to solve for t of n. The work that we're doing at that level is like do an if statement, figure out which branch to go down, and then we hand off the problem to t of n over 2. And so this goes down to t of n over 2, which again, assuming that's the recursive case, we're going to do constant work at that level and then hand it off to t of n over 4. Do you see that? Constant work at this level, hand off the work to t of n over 4. Which again, recursive case, does constant work at its own level and hands off the problem to t of n over 8. And so on and so forth, all the way down to, eventually, it's going to make its way down to t of 0, right? You're going to do integer division enough times to get to 0. And that, we have determined, is going to be constant work at the base case. So it's just a bunch of, again, it's a bunch of constant work, but the tree is not as high. You see that? The height here was n. What's the height for this one? How many levels are there here? Because I'm adding theta of 1. How many times? How many times can you have something and still have something left? It has to do with the logarithm, right? It's the log base 2 of n. That's how many levels there are. There might be like +1, -1. So it's roughly rounding log base 2 levels. And so this running time then becomes log base 2 of n times constant. And so theta of log base 2 of n is the answer. And so this is a logarithmic algorithm. See that? So that's binary search. Cutting stuff off in half. We know that to be a logarithmic algorithm, and that's how we can solve for that. We can legitimately do that for even the recursive algorithm. And then finally, for merge sort, we have this kind of thing. And so again, we're having, but we're like doing that twice. And then we're like, it's plus theta of n rather than theta of 1. How does that change things? Let's figure that out. So for merge sort, it was t of n is equal to 2 times t of n over 2 plus theta of n work, and then at the current level, and like this is the work at the smaller levels. And then eventually we're going to get down to the base case, which is constant, t of 0. So same style, we're asking for t of n. what's going to happen? Well, we're going to do theta of n work at that level, and then we're going to make 2 recursive calls this time. It's going to hand it off twice to t of n over 2. So there's 2 of them. T of n over 2 will do its own work. It'll do, well, if this input was n over 2, it's going to do n over 2 work at each call. It's going to be theta of n over 2 here, theta of n over 2 here for each call at their current levels. And then each of those calls are going to make their own 2 recursive calls to n over 4 amount of work, because you're dividing what you had by 2. So this is going to be theta of n over 4. See that? Theta of n over 4. Another n over 4 here. 2 more n over 4s. N over 4 work to be done. And then those keep on handing off work to like n over 8, n over 16. See that? And it keeps on doubling like that. So there's a lot going on. And eventually, we're going to get back down to, way down here, this is t of n over 4. It's going to go all the way down to the base case. Eventually, we're going to hit t of 0 if we divide by 2 with integer division enough times. So we're going to have a bunch of leaves. We'll think about how many in a second. And they're all going to be doing constant work. Right? That's what we determined. Whenever we hit the base case, we're doing constant work. So this is theta of 1, all the way down, theta of 1, dot, 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 dot. And so the question is, how do we solve how much work is being done? Because like we have to sum all these, plus all these, plus all these, plus all these. The secret, one of the secrets, is to notice, if I can move this to the left, that, ooh, this is not happy. Whee! One of the secrets is to notice that at each level, these all add up to n. See that? N over 4 times. Every time, like, the sum of all these adds up to n. So, like, this is still at this level, theta of n. This is at this level doing theta of n work. You see that? And so down here, even, down here, it's going to add up to theta of n work. And now the question is how many levels again? It's like how many times can you have something? Cut in half. Halve. H-A-L-V-E, the verb. How many times can you do that? It's log of n times. So again, log base 2 of n levels here. If I can write that and have it be visible still. And that's the secret. Like it's all together. Cool. So that is what you have to do. So at each level, we're doing theta of n work, and we have log of n levels. And so the algorithm's running time is, therefore, their multiplication. Theta of n log n. And so that's actually an optimal, one of the optimal sorting algorithms. So that's merge sort, and we have just like figured out how long it takes. It's great. Okay? So with that, hopefully you've kind of seen what happens. I want you to try. So give a recurrence relation for this min list algorithm. All right, give it a try. What's happening in the base case, what's happening in the recursive case. You can just like break it down into theta of stuff. That's what I was doing here. Draw the tree and see if you can, or I guess don't do the tree yet. Just give the recurrence relation. I think that's fine. That's plenty. And we'll do it a different way. We'll solve it in a different way. But like, what's t of n? In the recursive case, it's going to be, well, make the recursive call to a 1 smaller list. So that's t of n minus 1. Plus, like, do an if statement. Pick out some things. It's constant work in the rest. Constant work for the rest of the things. And then, like, what's t of, I guess it's size 1 this time. What's t of 1? That's the base case. How long does it take to do the base case? That is going to be constant work, right? Because it's just an if statement. And then, like, we're done. Give back the first element. That is the min. So that's going to be our recurrence relation. And yeah, I want you to just keep trying this. Try it for pseudocode now. I gave you real code. Try it for pseudocode. Give a recurrence relation for this. This is a divide and conquer, find the maximum function. You honestly don't really need to even worry why it's working or what it's doing, but try to give a recurrence relation that's going to talk about the number of operations performed on an input list with n items, let's say. So you're trying to find the maximum of a list of n items. Go through this and find the maximum, kind of like we were finding the minimum here. Is there any difference? It is doing some weird stuff. But you can assume that, like to make these lists, it's like constant time. It's like this is a recursive call, this is a recursive call. See if you can figure it out. It's like we're trying to figure out the time it takes to run find max on a list of n items, And so what happens is, well, if we're not in the base case, like this is a constant thing, we're checking an if statement, we're doing that, we're splitting up the list, assume that you can do that in constant time. We're going to make 2 recursive calls to lists that are half the size of each other. So this is kind of making a half the size list twice. So it's going down this half of the list, finding the max. It's a different way of finding the max than we found them in. And this is going down the other half of the list. So it's going to make a recursive call to half the size of the list, and it's going to make 2 of those. See that? That's the recursive case. Plus, and then like if statements, return things. It's all constant work at the end of that. So it's, let's just say like 1 there. And then the base case was the easy one. That was just, all right, in if the list size was 1, if let's say it's t of 1 then, it's pretty much, it's constant work. Just do an if statement and do a return. It's like 2 basic operations, and that's just like theta of 1. So there's that. And so we found these things. We found these recurrences. These are actually different from one another. Find max versus our find min was a little bit different. What's the running time of each of those? Let's try and figure this out. All right. So there, you can do it with a tree. You can totally do it with a tree. There's actually a secret. So I taught you the hard way because there's a cheating easy way. And here is that way. It's called the master theorem. So it's a little weird, but it's just like you just fill out a table. If your recurrence in your recursive case looks like this, t of n is equal to a times t to t of n over some b plus theta of n to the d, where these things can be variables, where a is greater than 0, b is greater than 1, d is greater than or equal to 0. So this could be theta of 1 because d could be 0. Then here is how you figure out the running time of your algorithm. It's like if this is true, this is your running time. If this is true, this is your running time. It's amazing. It's magic. It's called the master theorem. It works for anybody. All right. It solves all the recurrences that look like this, and most of them do. Okay. So let's confirm this with like merge sort and binary search, and you can try these after that. Let's see. I guess you can only do this one. You can't use this one because there's no dividing. So merge sort, its recurrence was this in the recursive case. It was t of n equals 2 times t of n over 2 plus theta of n. And let's confirm that that's n log n. So this is going to be like, how does this follow this? So what's a? A is 2, right? A is 2 and b is also 2. A is 2, b is 2. And then how does this turn into this? D must be 1 in that case, right? So D is 1. All right, so which of these are we in? It looks like b to the d is 2, right? 2 to the first power, that's 2. And a is 2, so we're in this one. A equals b to the d. And so we're, our algorithm is theta of, therefore, n to the d, which is 1, so just n, times log of n. Just like immediately gives it to you. It's amazing. So some very, very smart people out of MIT came up with this. And then for binary search, a little bit similar. T of n equals just 1 t of n over 2 plus constant work, right, each level. So how do we break this down? Again, we have, or not again, but for A we have 1 this time. For B, again, we're dividing by 2. So B is 2, and then D this time is 0, right, because we need 1 out of this. D to the n to the 0 is the only way we make 1. So how do we solve for this? What's B to the D? That's 1. And again, they're equal. So A is equal to B to the D. And so we solve for this. We get that the running time for binary search, recursive binary search, is theta of n to the D, which is just 1, so that kind of goes away, times log of n. So it's just 1 times log of n or log of n. And so that's our binary search running time. That's the master theorem, and it does it all for you. It's so nice. And so, yeah, before we go, for our last slide, let's talk about how to use the master theorem for just like, if you get these problems that look like this on a test, like you can just plug and chug. It's really not hard. So just like think about what A, B, and D are, solve for them, and we'll check our answer. So give that a try. All right, I'll try to make this easy for myself by writing this out and just copying and pasting it a couple times. What is A and B and D for all these? A, B, D, A, B, D. and then we'll just do it quickly. So, all right. A for this one is 2, B is 3, and D is 1. 2, 3, 1. See that? 2, 3, 0 this time. 2, 3, 0. 7, 4, 2. And 7, 4, 1. Let's see how that changes things. So if these are our algorithms, whatever they're doing weird stuff, you can come up with some algorithm that works like this, I guess. Let's see their running time, if this is their recursive cases recurrence relation. So, okay, it's always having to do with b to the d. So b to the d is 3, and a is 2, so it's like this, a is less than b to the d. So therefore, it is theta of n to the d, and d is 1, so theta of n for that one. B to the d here is 1, and a is 2, so a is bigger than b to the d for this one, so it looks a little weird. It's going to be theta of n to the log base b, log base 3 of a, of 2. So that's an interesting exponent, but that's apparently the answer there. So I think that's that one. And then let's look at this one. B to the d here, 4 squared is 16, a is 7, so it's smaller. So we have theta of n to the d, which is 2. N to the d is 2, or sorry, d is 2, so n to the d is n squared. Theta of n squared for that one. So this is somehow an n squared algorithm. Crazy. It's like this one wins somehow. And then finally this one, let's see what happens there. So we have b to the d is 4, a is 7, so 7 is bigger than 4. So we're in this case, so we're in this weird looking one again. So this is theta of n to the log base b, base 4, of a of 7. So that's another weird exponent. But that is, whatever that is the answer. And so the master theorem is very powerful, very cool, and gets the job done very quickly. But if you have a more generic, if you want to try to understand it a little bit better, I would encourage you to try making these trees for things, and that will help you solve some of them, like our minimum one. This ends up being like, this is the same as factorial's recurrence, and the master theorem doesn't really apply when you're doing like n-1 stuff. So you're going to have to solve that one by hand or with a different method. But with master theorem, if you have like n over something, it'll just solve it very quickly for you, and that's really nice. So yeah, we covered a lot of ground today, talking about how to prove that recursive algorithms are correct. It's a really, really cool thing to do. And now you are good at it. So I'm going to ask you to do that kind of stuff in your homework and practice it a whole lot. But that's as many words as I want to tell you in one lecture. So thank you for your attention, and I will see you next time.